Hello students, today we will have the online chemistry class for class 12. Due to COVID-19, we cannot have the normal scheduled classes as usual. So we are taking the help of the online classes this year to complete the syllabus. I hope that the way of teaching is helping you at this situation, and I advise all my students to stay home and to stay safe. We will today read the chapter Chemical Kinetics from Physical Chemistry. In this chapter, we will mainly read about the rate of a chemical reaction. Now, what do you mean by the rate of a chemical reaction? Rate means the speed with which a chemical reaction is occurring. In chemistry, we are reading every day thousands of chemical reactions, and in fact, chemical reactions are occurring beside us in lab everywhere. Now, if we want to determine the speed with which each and every reaction is taking place, that is the rate for a reaction. Based on the rate, we will learn about the factors affecting the rate, different types of rates, the graphical representation, integrated form of different order reaction, zero order and first order reaction, Arrhenius equation, and all the numericals based on these theoretical portions. So as I told that we have to determine the rate of a reaction in this chapter. Mainly there are three types of reactions around us. One is very fast reaction, another is very slow reaction, and the third one is moderate speed reactions. Now you see the reactions that we do in the lab. Suppose we are adding ammonium hydroxide solution in copper sulfate solution. We can see that we get a pale blue PPT instantly. That is, as soon as we add one reagent to the other, we get the precipitate. This type of reactions which takes place within a fraction of time is a very fast reaction. Next comes very slow reaction like rusting of iron. We know that when iron is left in free atmosphere, gradually with time it gets rusted. But we don't know that what is the exact time needed for iron to get rusted. So this type of reactions where we don't know the time and it's a very slow process, in this case also we cannot determine the rate. For very fast and very slow reaction, as the time we cannot determine exactly, we cannot determine the rate. So the left behind part is the moderate speed reaction, that is for which a definite time is there, maybe 10 minutes, maybe 1 hour, maybe 2 hours, maybe 30 minutes, whatever it is. The time is measurable. So for those type of reactions, we will determine the speed of the reaction, that is the rate of the reaction. How we represent the rate of a reaction? You see, when a reaction is starting, gradually with time, the amount of the reactant is reacting to produce product. So the concentration of the reactant is decreasing and the concentration of product is increasing. So if we plot concentration of reactant and product with time of reaction, the concentration of the reactant will decrease and the concentration of product will increase. Okay, so this is the graphical representation where this is the product and this one is the reactant, because with time reactant is getting used up, reacting and producing the product. Now suppose a reaction is taking place, AA plus BB producing CC plus DD, where the small a, small b, small c and small d are the stoichiometric coefficient. What do you mean by stoichiometric coefficient? The balance. When we are writing a chemical equation, we are always balancing the equation with whole numbers, maybe 2, maybe 3, maybe 4, maybe 5 as required for the reaction. So those whole numbers which are written in front of the reactant and the product are known as stoichiometric coefficient. Capital A and B are the reactant, capital C and D are the product. So I have to represent the rate. Rate is equal to minus 1 by A change in concentration of A by time taken, or -1 by B, change in concentration of B by time taken, or 1 by C, change in concentration of C by time taken, or 1 by D, change in concentration of D by time taken. So from these we can see that the stoichiometric coefficient is represented as 1 by. So whatever number we will have in the balancing, it will be the denominator portion. Then delta represents the change, how much reactant or how much product has been produced or consumed up. Reactant, for reactant it will be consumed up, for product it will be produced. And whatever thing we write inside a third bracket, inside third bracket representation means it is representing the concentration of the reactant and the product. So this is the rate of a reaction. Now rate can be of two types. One is average rate, another is instantaneous rate. One is the average rate, another is the instantaneous rate. What do you mean by the average rate? Average rate means in a given period of time how much reactant is consumed up or how much product has been produced. So it is told that the time for a complete reaction is equal to 1 hour. And suppose I have taken a reactant X. At the time of the reaction, the concentration of X was 5 mole per liter. And after the reaction, the concentration of X1 I am representing, it became 2 mole per liter. So in the total process, the total time is 1 hour, and how much amount of the reactant has been consumed? 5 minus 2, 3. So the average rate will be equal to 3 by 1 mole per liter per hour. So this is the average rate which is representing the total, in the total reaction in a given time how much reactant has been consumed. But for instantaneous rate means the rate of a reaction at a particular instant. Suppose for this reaction only, it is given in the question that what is the rate of the reactant reacting at 10 minutes. So when the reaction has been completed up to 10 minutes, at that point, what is the rate of the reaction? So at a particular instant, what is the rate of the reaction is given by the instantaneous rate. At a particular instant, what is the rate? So this is the basic difference between average rate and instantaneous rate. Next, factors affecting the rate of a reaction. There are several factors which can affect the rate of a reaction. Number one, it can be the concentration of the reactant. More the concentration of the reactant, more will be the rate of the reaction. Why? Because the number of collisions among the reactant molecules increases. Next, temperature. More the temperature, more will be the reaction rate, again for the same reason. Whenever we are increasing the temperature, the energy provided to the reactant molecules increasing, and so the rate of the collision will increase. Third comes the surface area of the reactant. Here also, more the surface area of the reactant, more will be the reaction rate. Suppose I have taken one glass full of water and I have left it for evaporation, and that same glass of water I poured it in the floor and I am expecting to evaporate. Which one will be evaporating at a faster rate? The water that I poured in the floor. Why? Because when I am pouring it on the floor, it is getting a large surface area compared to the water which is confined in a glass. For that reason, more the surface area, more is the scope of the reactant molecules to interact with the atmosphere, so more will be the rate of evaporation. Same for the reaction. Whenever the surface area is more number of molecules are getting to interact, and so the more reaction rate will be there. Now, if I focus on the first factor, that is the concentration of the reactant, then we will get two laws. One is law of mass action, and another is rate law. Why I am studying the two laws at a time? Because both the laws gives us the same thing, dependency of the concentration of the reactant on the rate of the reaction. How the concentration of the reactant is affecting the rate of a reaction is given by law of mass action and rate law. Both the laws states nearly the same thing, only a minute difference is there. This is a theoretical concept and this is a practical concept. Practical means experimental fact. That is, we find out the rate of a reaction by experimentally doing it, and we find out the rate of a reaction by theoretically calculating it. So one is the experimental law and another is the theoretical law. What law of mass action states? Law of mass action states that the rate of a reaction is directly proportional to the active masses of the reactant with the stoichiometric coefficient raised to the power. Suppose I am doing a reaction AA plus BB producing CC plus DT, same way. Now law of mass action states that rate of this reaction is proportional to the active masses of the reactant. Both A and B is the reactant. And what do you mean by the active mass? Their concentration in mole per liter. So whatever amount of A and B I am taken, they are having a definite concentration. So active mass means their concentration when represented in mole per liter. So law of mass action states that the rate is directly proportional to the active masses of the reactant with the stoichiometric coefficient raised to the power. So A to the power A, B to the power B. So law of mass action states that. Same thing rate law also states, but the basic difference is what I am coming in a detailed way. Suppose one reaction, the overall reaction is represented as 2A plus 3B producing 4C plus D. Now you see, in practical life, when a reaction is taking place, we don't know that the reaction is taking place in 1 step, 2 step, 3 step or multiple steps. Many reactions takes place in one step, but many reactions do not take place in one step and they can involve many steps within. So let us consider that this is the overall reaction, but the reaction has taken place in these 3 steps. Step 1, step 2 and step 3. And if we overall calculate these 3 steps, we get the first reaction. Now according to law of mass action, it is a theoretical concept. So it will see that what is the reaction given? This is our reaction. So according to the law of mass action, rate will be proportional to A square and B cube. But rate law states that, what rate law states, when a reaction is taking place in multiple steps, the rate of a reaction depends on that particular step, which is the rate determining step. RDS. You know what is a rate determining step as you have learned it in class 11. So out of the 3 steps, one particular step is the slowest step and that is the rate determining step. Say this is our rate determining step, RDS. So according to rate law, the rate of the reaction will be dependent upon the reactant molecules involved in the rate determining step. So the rate will be proportional to the concentration of A into concentration of B. So you can see that there's a huge difference between this rate expression, and which one is correct? Obviously the rate law. So the finest definition of the rate is depending upon the concentration, that the rate of the reaction is proportional to the active masses of the reactant with the stoichiometric coefficient raised to the power, but in which step? In the rate determining step. So when the reaction is taking place in multiple steps, the one particular step which is the RDS, in that step the reactant molecules involved, in those reactants the rate is dependent, not in all. Okay, so this is the basic difference. Now in general, if we remove the proportionality constant, then we can give a constant, and that is K given in every cases. And what is K? K is our rate constant, which is having different unit for different types of reactions. Now what different type of reactions? I will learn on the topic order and molecularity of a reaction. So next I will come to the topic order and molecularity. What do you mean by order of a reaction? Order is the number of reactant molecules involved in the rate expression. So you see in this case how many reactant molecules are involved? 2. So what will be the order of the reaction? 2. Now if in any reaction the reactant molecules involved are in this expression A square B cube, then how many reactant molecules involved? I will add the coefficient 2 plus 3 5. So the order will become 5. So based on this concept we can have many types of order. Number 1, many reactions can be zero order reaction. Example, hydrogen and chlorine reacting in presence of sunlight to produce 2HCl. This is a zero order reaction because it has been seen that the rate is neither dependent on hydrogen not dependent on chlorine. It is independent on both the reactants. So the type of reactions which are not depending on any of the concentration of the reactant, the rate is not dependent, that type of reactions are called zero order reaction. Why they are not dependent? Let me explain this one. This reaction is generally taking place in a sealed tube. In a sealed tube, below water is there and above water a mixture of hydrogen and chlorine gas is present and the reaction is taking place. Now as the reaction is taking place, HCl is produced, hydrogen chloride gas, and I know that, we all know that hydrogen chloride gas is a highly soluble gas in water. So gradually with the formation of HCl, it gets dissolved in the water and the water level rises. But as all over the container is sealed, the concentration in mole per liter remains the same. As with the reaction the concentration do not change, so the rate of the reaction is becoming independent of the reactant. So this type of reactions are zero order reaction. Number 2, fast order reaction means where the reaction is dependent upon only one reactant. Suppose I am decomposing hydrogen peroxide. So what we will get? H2O plus half O2. So here the rate is equal to the rate constant and only the concentration of H2O2. So how many reactants are involved? Only 1. So the rate order of the reaction is becoming 1. So like this there can be second order reaction, there can be third order reaction. Another different type of reaction, it can be fractional order reaction. In some cases the order is becoming fractional. Example, when hydrogen reacts with bromine, it produces 2HBr. But from experimental data in this reaction, rate is equal to the rate constant, concentration of hydrogen and concentration of Br2 to the power half. So you see here the order of the reaction is becoming 1 plus half, that is 1 and a half, a fraction. So some reactions can be fractional order reaction. Next, another different type of reactions order is there, that is pseudo fast order. What is the meaning of the word pseudo? Something hidden. See, one example is hydrolysis of cane sugar. In this process, when we do the reaction, when we hydrolyze a cane sugar, the amount of the cane sugar and the amount of the water is a large difference. Suppose we have taken this much amount of cane sugar in a huge amount of water. So the concentration difference between the water and the cane sugar is so high that the concentration of one reactant cannot affect the concentration of the other. So in this case, the rate of the reaction is depending upon any one concentration, either of the cane sugar or of the water. As the difference in the concentration in both the reactants are so high, so though two different reactant molecules are involved, but only on one reactant molecule the rate is dependent. So one is just avoided. For this reason the word is coming pseudo fast order. Two are there, but the rate is affected by only one. So these are all about the order of a reaction. Now I will come molecularity. Molecularity is a bit different from that of the order. Molecularity is the number of molecules involved in a particular reaction. To explain this, I will come to a previous topic. Here you see, in this reaction, as I told that, the overall reaction is this one, but it took place in 3 steps. Molecularity tells that molecularity is different for each step. So for this reaction, on the first step, the molecularity is 2 because 2 molecules are involved. In the second step also, the molecularity is 2 because 2 molecules are involved. But in the third step, the molecularity is 3 because 2b and 1f, so total 3 molecules are involved. So molecularity means number of the molecules involved in a reaction in each and every step. So molecularity do not hold for an overall reaction. If the reaction is taking place in one step, then it can be. But when the reactions are taking place in different steps, the molecularity is different for each and every step. So in simple words, molecularity means the number of molecules involved in each step. And like order, molecularity can never be 0 or in fraction. It is always a whole number. Another thing I will learn in this, I will tell you in this class, and I will end this class, that is the unit of the rate constant. See, for 0 order reaction, what will be the unit of the rate constant? Unit of K. Here, in 0 order, the rate of the reaction is independent on any of the concentration. So we can tell for 0 order, rate is only equal to rate constant. And what is the unit of rate? Change in concentration, that is mole per liter with time. So mole per liter per time. Change in concentration by time, that is mole per liter per time, is the unit of rate, and that only will be the rate of unit of the rate constant. But for first order reaction, as I know that rate is equal to the rate constant and any one reactant species, anything. So K is equal to what? Rate. And what is rate? Mole per liter per time divided by the concentration of the reactant, and any concentration is expressed here in mole per liter. So mole per liter get cancelled out, and for a first order reaction, the unit of the rate constant is becoming time inverse. For a second order reaction, we can write rate is equal to the rate constant K into, it is dependent upon any 2 concentration. It can be A into B or A square also. So K is equal to, what is the unit of rate? Mole per liter per time divided by, there will be 2 concentrations. So mole square liter to the power minus 2. So what we will get? Mole inverse liter time inverse. So you see, the unit of the rate constant is different for different types of reactions where the order is changing, and so in different numericals, when the order of the reaction is told to be determined, we can do it from the unit of the rate constant. If rate constant is given, then from its unit we can directly understand that what is the order of the reaction. So up to the order and the molecularity, I will end my first class. Based on these, I will give you some homework, numericals to do at home. On my next class, I will continue the 2 more topics, that is integrated form of the 0 and the first order reaction and Arrhenius equation.